Alright, here we find ourselves in 2.5. The big idea in 2.5 is this idea of bearings, and there's multiple ways to express bearings. So a bearing is an important concept used in navigation, and it's measured in a clockwise direction, not counterclockwise. And so um, uh, bearings are always from due north. So if we look at the 33 degrees, right, you can make that bigger, that's nice. 33 degrees, if that's the bearing, if they say the bearing is 33 degrees, it's always from due north, and it's 33 degrees off of due north. It would be heading in that direction. So 164 degrees, always from due north, not from the x-axis, but from the positive y-axis, and we're always moving in a clockwise direction. And so here would be 90 degrees, and here would be 180 degrees. We're in between there, right? We're at 164. So this is 164 degrees, just to show that out. 229 degrees, well, that's more than 180. It's always off of due north, so it's going to rotate more than halfway around, but not quite to the 270 mark, so it's going to be off this way, where it's 229 degrees. So if a ship's going at a bearing of 229, they're headed in this southwest direction. At 164, they're heading in a southeast direction, right? And if it's 33 degrees, they're headed in a northeast direction. It's 304 degrees. If the bearing was 304 degrees, well, that's more than 270, not quite 360, right? So it's out over here, 304 degrees. Right? And so once you have an idea of bearings, it's going to come up in some problems. They'll maybe have us draw a few in the homework. There's also another convention. What's above is true bearings. This is conventional bearings, and they talk about heading east of north and east of south and west of north. You know, that type of thing. That's what we want you to read that as. So they use the north-south line, so they're using the y-axis for bearings, which is different than our angle measurements, right? They were always off of the x-axis, but these are off of the y. So if you have a north 42 degree east, it means off of north, head 42 degrees east of that. So what does south 31 degrees east mean? And you can see why they're going to use them. It means off of the south direction, head 31 degrees to the east. Or off of the south direction, travel 40 degrees to the west. No problem. Here's the south direction. And go over here 40 degrees. And that way your angles can stay actually acute, right? They can stay under 90 as you use this method. And so I think that's why it's conventional, is because you don't have to state huge degrees. North 52 degrees west, well, it's off of the north, and we need to head 52 degrees. Actually, 52 would be wider than that. 45 is what I appear to have drawn. But 52 would be a little bit more than halfway. 52 degrees. So we want you just to understand those. There's clear copies in the book of this. Let's take a look at this. An observer at a radar station is located at the origin. Find the bearing of an airplane located at 2-2. Express it using both methods. Okay. No problem. So let's draw a picture. Now this is related to homework problem, in this case problem number 12. And let's go ahead and draw. We know where 2-2 is. No problem. And we're headed in this direction. And they want to know, well, what is that? Well, what degree would that be? No problem. One method is to figure out if we're doing the true bearings, how far it is off of north. So we really want to know what is, let me put it in red. Red's what we want in this case. They're basically asking, what is this angle? That's what we need for true bearings, and we always go off of that north line. Well, no problem. You have a 2-2 relationship here. If we can figure out this angle, we can know the other. Well, tangent of this angle that's inside, I'll call it theta, is equal to 2 over 2, or tangent theta is equal to 1. Well, you know what angle we can take the tangent of to get 1. It's 45 degrees. So 45 degrees is inside that triangle, but then 90 minus 45 degrees is outside that triangle, which is what we want. So we have a bearing of 45 degrees. That's the true bearing way. Then they have the conventional. So if we go do the conventional over here, what are we going to do? So if we could easily say something like this: north 45 degrees east. That would be the best way to express that. You want to look for the small angle that's created between the y-axis. You don't want to go south because then you're having to create a big angle. You want to do it as efficiently as possible. North 45 degrees east. So I hope that makes sense, but let's see if it does. Let's go and look at something like, so you can get an idea. Let's change something. Same question, except I'm going to change the point. Instead of 2, 2, let's look at the point 2, negative 2. Let's have it be out in a different quadrant. Now they're picking things where you know the tangent of them. So if it's 2, negative 2, here's 2, negative 2. We're headed in this direction right here. Well, what is that? The true bearing. Let me put that in red again. This is the true bearing. What is this? Whatever that is, that's the true bearing. Well, what we do know is we're going to have the same relationship of negative 1. And so this right here is going to be 45 degrees. So what is this? This is 135 degrees. And so we have 135 degrees, right? Because we got to get to 180. So 135 degrees is right here. That's the true bearing. Now, what's a great way to express this? South 45 degrees east, right? I'm from a south direction, head 45 degrees to the east, would also end up there. So I just wanted you to see a companion to that. And you'll see it in the homework as well. Uh-oh, we got two ships leaving a port at the exact same time. The first ship sails on a bearing of 52 degrees at 17 knots, and the second on a bearing of 322 degrees at 22 knots. How far apart are they after 2.5 hours? Okay. We just have to draw a picture and keep everything straight. They are going to be big problems, but that's why you're taking this big major, right? You're signing up for a big major because you want to be able to think this way. So here we go. We start with the picture of what's going on. We have two ships. One's heading at a bearing of 52 degrees. So we'll head 52 degrees off of north, and we are heading in this way. Okay, that is the first ship, so I'll call it ship A. And it's traveling, like it says, at 17 knots. We'll get to that. The second is on a bearing of 322. So 322 is a long ways around. It's more than 270. It's almost 360. It's way over here. That's ship B. And it's traveling at 300 and... I'm sorry. I said traveling at... So it's that 332. So that's ship B. And what do they want us to find? Let me put in red what they want us to find. They want to know this distance right here. 2.5 hours into it. Okay, 2.5 hours, what's this x? Well, in 2.5 hours, how far is ship A gone? No problem. So ship A, remember, distance is equal to rate times time. So the distance traveled by ship A, it's going at 17 knots. And it's doing that for 2.5 hours. And so the distance it travels is 42.5. That's how far it's traveled. and they're nautical miles. That's what knot stands for. So this is a speed. It's a nautical knot per hour. A nautical mile per hour. Apologize. And so this right here is 42.5. Let me just write it in there. That's the length of that line. What's the length of this other line? No problem. For ship B, distance is equal to rate times time. It's traveling at 22 knots for 2.5 hours, so it's farther out. Makes sense. And what are we going to get out of that? We're going to get a nice 55. Perfect. So we got two sides of this triangle that are here. And so how do we figure out what to do? Well, we got a little bit of a problem. We have a huge problem unless a miracle works out. And so let's see if a miracle works out. So the huge problem that we're going to have is we can't use any of our trig relationships. We can't even use the Pythagorean theorem unless we know this is a right triangle. And if it's not a right triangle, well, we don't know what to do yet. We'd have to use something like the law of sines or the law of cosines, and it's a different process. I was going to say a more lengthy process. It's not necessarily more lengthy. So let's see something, though. Did they create a miracle? Did they give us the perfect math problem? What's this angle right here? Let's find out what that angle is. So if we go to find out what that angle is, let's remember something. I'll put it in red. That this angle right here was 322. Now to go all the way around would be 360, so that blue area, let me just put that like that. The blue area is equal to the 360 degrees minus the 322. And what is that? What's 360 minus 322? You might not think it's impressive. It's only 38. But let's put 38 in there. So the blue angle is 38. Tell me, what's 38 degrees plus 52 degrees? 90 degrees. They created a miracle. This is the reason why we can do this problem, and why it's not in chapter 7 is because it's not just any old triangle. It's a right triangle. And so they created that miracle, as math books often do. And here we go. You know exactly how to find that x. You don't need trig. You don't need anything. Now, we needed a trig for the bearings because they never taught us that before. But it's not necessarily a trig principle. And this all worked out to be a right triangle. Well, I can ask a pre-algebra student how to solve for x. They know that in a right triangle, 42.5 squared plus 55 squared needs to be equal to x squared. And they would find x just like that by taking 42.5 and squaring it, adding 55 squared, and coming up with their answer of 4831.25 is equal to x squared, and then they would square root. Now, we wouldn't give them such big numbers. 69.5 nautical miles. That is what that length of x is. 69.5 nautical miles. So pretty involved, right? But not, using some old stuff. So this is very representative of your future math. They never talked to us about distance is equal to rate times time. They never talked to us about knots necessarily. They just expect us to know. Why know this? Because it's been taught since our arithmetic days, our pre-algebra days. Expecting us to be able to solve a right triangle where two sides are known. No, that's been an expectation since pre-algebra. They will not necessarily reteach the old stuff. They'll just bring it up in context. And so now we got Debbie Glockner-Ferrari, a whale researcher, is watching a whale approach directly towards a lighthouse. When she first begins watching the whale, the angle of depression to the whale is 15 degrees 50 minutes. Just as the whale turns away from the lighthouse, the angle of depression changes to 35 degrees 40 minutes. If if the height of the lighthouse is 68.7 meters, find the distance traveled by the whale as it approached the lighthouse. Okay, this is a very common problem. And so we want to draw a picture. It comes in varying forms, and it's going to be involved. So hang with it as we go through here. We're going to need all of this space. So the first part that we're going to do is come over here and draw our picture. So what do we have? We have a person who's watching a whale approach towards a lighthouse. And when she first begins watching the whale, the angle of depression to the whale is 15 degrees 40 minutes. Just as the whale turns away, the angle of depression. If the lighthouse is 68.7 meters, find the distance traveled by the whale. So here is the lighthouse at 68.7 meters tall. Remember what an angle of depression is. It's off of this guy. And so when she first begins watching the whale, the angle of depression is 15 degrees 50 minutes. So I'm going to come in here. I'm going to draw a line that goes way out here. And this angle right here is 15 degrees 40 minutes. So notice they're keeping the degrees and minutes alive. So 15 degrees 40 minutes is in there. It changes, right? A little while later, she sees it swimming towards it, and then she sees it turning away. And when it turns away, it was at 35 degrees 40 minutes. So I'm going to come out here and make it a little bit different. But this angle right here, let me do it in a blue color. Oops, sorry, it didn't change the color. Let me do something right here. So this is 15 degrees 40 minutes, and this angle right here is 35 degrees 40 minutes. Okay, awesome. And then what are we being even asked to find? Just draw a straight line over there and go back to my eraser, and let me just make it a pixel eraser here for a minute to get rid of those bottom lines, make it a little bit more clean. We're being asked to find this, x. X is the distance that the whale traveled. Y then, let me call this y. We're going to have to deal with a couple of triangles, maybe even 3. Y is the distance between the whale between the tower and the churning whale, right? The tower and the churning whale. So yes, you're going to be expected to do this, and now we got to creatively figure out how in the world are we going to come up with x. What can we get out of this stuff that's going to be able to help us out? And so we need to figure out how in the world we can use this 68.7. And so what angle would we need to be able to identify? We need to be able to identify maybe this angle right down here. Do you happen to see what that would be? You could use an old technique, or we could just keep doing good stuff, right? Let's talk ourselves through this. Now, what I mean by good stuff is just crank it out. So there's always more than one way to approach a problem. I really want to know what this angle is right here, or this one right here. Either one would help me out. But I focused on the bottom one. I'm not sure why. It doesn't necessarily matter. Maybe it does, as I think about it a little bit more, but that's the one I want to find. Well, you have two parallel lines being cut by a transversal. This angle right here has to be the same 35 degrees 40 minutes. That could be some person's argument. Another person might say, well, I would find the makeup from here to here by taking 90 away from it, but then you'll quickly find out this is the same angle because these two angles have to add up to be 90. And so through either argument, we know that this is 35 degrees 40 minutes. Sound all right? So there's a few ways to find it. So let's talk about this. We got the The tangent, then, of 35 degrees, 40 minutes, needs to be equal to the 68.7 over y. So what y then is 68.7 divided by the tangent of 35 degrees 40 minutes. Right? If you picture that movement, moving the y over to this side, bringing the tangent back, that's what it would be. So let's find out what y is. 68.7 divided by tangent of 35 degrees plus 40 divided by 60. We've done that before. And we get a 95.7. We'll keep the same area. And I've watched books not degrees, 95.7 feet, right? Is everything in feet? 95.7 meters, sorry, everything's in meters. So I've watched some books actually not figure that number out, just keep that in mind. So we want to know what x is. Well, we're never going to be able to work with that x. If you look at, let me shade it in. Actually, let me use this to shade it in. If you look at this triangle right here, right, this guy right here, we're never going to be able to work with that lone triangle. And the reason why is there's no right angle in it. We want to have triangles with right angles. So what we're going to look at right now is the big triangle. Let me highlight the big triangle. We're going to look at the big triangle because that has a right angle in it. So let's talk about that. What's this angle? What's this angle right here? Well, it's got to be, these are two parallel lines. Here's two parallel lines, the base of the triangle and the horizontal being cut by a transversal. This has to be 15 degrees 40 minutes. So we know the tangent of 15 degrees 40 minutes needs to be equal to the 68.7, that's on that side of that triangle, all over y plus x. Or, no, darn, sorry about that. Okay, we'll get back up there. It's too exciting not to get back to. Okay, you can see the stuff that we're going to get into. All right, 68.7. So we're going to multiply both sides by y plus x. And that's the tangent of 15 degrees 40 minutes is equal to 68.7. You're just going to use your great algebra skills, or y plus x is equal to 68.7 divided by the tangent of 15 degrees 40 minutes. Remember, we're solving for x. That's our whole goal, is to solve for x. And so as we go solve for x, I did it again, I'm too far over to this side. As we solve for x, x is equal to this 68.7 all over tangent of 15 degrees 40 minutes minus y, but we know what y is. 68.7 all over the tangent of 15 degrees 40 minutes minus y. Oh, I apologize. We know what y is. I meant to replace it. What is y? 95.7. Sounds like a radio station. 95.7. So what are we going to do? We're going to take 68.7 on our calculators, divide by the tangent of 15 plus 40 divided by 60 minus 95.7, and we'll get an answer. And our answer is x is about 149. Now, I'm interested, what if I never rounded? What if I just took the 68.7 divided by the tangent of 15 plus 40 divided by 60 and subtracted away 68.7 divided by the tangent of 35 plus 40 divided by 60. How close would I be? Yep, pretty much the same. 149. coming out of there. So it doesn't seem to make any difference that we rounded that off to begin with. 149 meters is how far that whale swam in that time period that she was watching it swim towards and then turn away, and noting those angles of elevation. There'll be other similar problems like this. They're good. They're really good homework exercise questions to go through, because they're good thinking problems. Again, we've picked the two triangles that we did because of this right angle right here. Because that was 90 degrees, it made us be able to work with the trig. And you can see that tangents used a lot. I don't think